We have seen several situations where we want to store a sequence of values. Now, it turns out that in a program or in a programming language implementation, there are two basic ways in which we can store such a sequence. These are normally called arrays and lists. So, let's look at the difference between arrays and lists. So, an array is usually a sequence which is stored as a single block in memory. So, you can imagine, if you wish, that your memory is arranged in a certain way, and then you have an array. So usually memory is arranged in what are called words. So a word is one unit of what you can store or retrieve from memory, and an array will usually be one continuous block without any gaps. And in particular, this would apply when an array has only a single type of value. So all the elements in the sequence are either integers or floats or something where the length of each element of the array is of a uniform size. And we would also typically in an array know in advance how big this block is. So we might know that it has, say, 100 entries. So we have a sequence of size 100. Now when this happens, what happens is that if we want to look at the jth element of a sequence or the ith element of a sequence, then what you want to think of is this block of memory starting with 1, 2, 3 up to I, right? And you want to get to the ith element quickly. But since everything is of a uniform size and you know where this starts, you know where the sequence starts, you can just compute I times this size of one unit and quickly go in one shot to the location in the memory where the ith element is saved. So accessing the ith element of an array just requires a computational arithmetic computation of the address by starting with the initial point of the array and then walking forward I units to the ith position. And this can be done in what we could call constant time. By constant time, what we mean is it doesn't really depend on I. So it is no easier or no difficult to get to the last element of an array as it is to get to the second element of an array. It is independent of I. It takes a fixed amount of time to get to sequence of I for any I. Now, one consequence of this is inserting or contracting arrays is expensive, because now if I have an array with 0 to 99 and I want to add a new value here, say at position I, then first of all this array now becomes from 0 to 100, and now everything which is after I has to be shifted to accommodate space if we want to keep the same representation where the entire array is stored as a single block. So when we have a single block of memory, though it is efficient to get to any part of it quickly, it is not very efficient to expand it because we have to then shift everything. The worst case, for example, if this green block comes at the 0th position, then the entire array has to be shifted down by one position. In the same way, contraction is also expensive because we have to make a hole in some sense. So if we remove this element out, then we have a hole here, and then we have to push everything up to block this hole, because remember the array must have all elements contiguous, that is without any gaps, starting from the initial position. So the other way of storing a sequence is to store it one element at a time and not bother about how these elements are with respect to each other in the memory. So I can think of this memory as a large space, and now I might have one element here. Okay, so this is my first element, and then I will have a way of saying that from here the next element is somewhere else. So this is what we call a link. So very often in the implementation, these are called linked lists. So I might have the first element here. Now because of various reasons, I might end up putting the second element here, and so on. Right? So this, you can imagine that, if you have some, say, a space in your cupboard, and then you take out things and then you put things back, but you put things back in the first place where you have an empty slot, then the sequence in which you put things back may not respect the sequence in which they appear finally in the shelf. So here in the same way, we don't have any physical assumption about how these elements are stored. We just have a logical link from the first element to the next element and so on. So the other part of this is that we don't have to worry about the overall length of the list, because we know we start at the 0th position and we keep walking down, and the last position, so say suppose the last position is in fact 2, then there would be some indication here saying that there is no next element, so 2 is the last element. So a list can have a flexible size, and obviously because we are just pointing one element to another, we can also accommodate what we see in Python, where each element of a list may be of a different type, and hence each value might have a different size in itself. It's not important, unlike an array, that all the values have exactly the same size, because we want to compute how many values to skip to get to the ith element. Here we are not skipping, we are just walking down these links. So since we have to follow these links, the only way to find out where the ith element is to start from the 0th element, then go to the first element, then go to the second element, and so on, because a priori we have no idea where the ith element is. So after I steps, we will reach the ith element. And if we have a larger value of I, it takes longer to get there. So accessing the ith position in a sequence when the sequence is stored as a list takes time proportional to I. We can't assume that we can reach any position in the list in constant time, unlike in an array. On the other hand, it is relatively easy to either insert or delete an element in a list like this. So supposing we have a list like this, so supposing we start at the 0th position, we come to the ith position, and currently if we say that the ith position points to the I plus 1th position, which points to the rest, and suppose we want to insert something here, then it's quite simple. We just say that this is the new I plus 1th position. So we create a new block in memory to store this value, and then we'll make this point here. So it's like plumbing. We remove one pipe and we attach a pipe from the ith element to the new element, and we attach another pipe from the new element to what was beyond the ith element previously. So we just have to shift these three links around, and this doesn't matter wherever we have to do it. Any place in the list, if we just have to make this local change in these links. And so this insertion becomes now a constant time operation if we already are at the position where we want to make the change. In the same way, if we want to delete something, that's also easy. In fact, it's even easier. So I have, say, I pointing to I plus 1, pointing to I plus 2, and I want to remove this element. Well, then I just make this link directly point to the next one. Remember, all these links are available to us. We know this link, we know this link, so we know where the I plus 2nd element is. Similarly here, when we want to create a new element, we get a link for it because we create it, and we know what link to copy there because we already have it here. So we can copy it from the ith element to the new element. So therefore, in a list, it is expensive to get to the ith element. It takes time proportional to the position we are trying to get to. However, having got to a position, inserting or deleting an element at that position is of constant time. Unlike in an array, where if we insert or delete at some position, we have to shift a lot of values forwards or backwards, and that takes time. So let's look at typical operations that we perform on sequences. So one typical operation, now if I just represent a sequence more abstractly as a sequence as we have been drawing it. So supposing I want to exchange the values at I and j. So this would take constant time in an array because we know that we can get the value at the ith position, get the value at the jth position in constant time, independent of I and j, and then we exchange them, which just involves copying this there and the other one back. On the other hand, in a list, I have to first walk down to the ith position and then walk down to the jth position to get the two positions. So I will have in a list, I would have a sequence of links, and then I would have another sequence of links. And then having now identified the block where the ith value is and the block where the jth value is, then I can of course exchange them without actually changing the structure. I just copy the values back and forth. But to find the ith and jth values, it takes time proportional to I and j. So it takes linear time. On the other hand, as we have already seen, if we want to delete the value at I, position I, or insert a value after position I, this we can do efficiently in a list because we just have to shift some links around. Whereas in an array, we have to do some shifting of a large bunch of values before or after the thing, and that requires us to take time proportional to I. So the consequence of these differences between the two representations of a sequence as an array and a list is that we have to be careful to think about how algorithms that we want to design for sequences apply depending on how the sequence is actually represented. An algorithm which works efficiently for a list may or may not work efficiently for an array and vice versa. So to illustrate this, let us look at something which you are probably familiar with, at least informally, called binary search. So the problem we are interested in is to find out whether a value v is present in a collection, or we can even call it a sequence to be more precise, in a sequence which we call SEQ. So we have a sequence of values, we want to check whether a given value is there or not. For instance, we might be looking at the list of roll numbers of people who have been selected for a program. We want to check whether our roll number is there or not. So there are two questions that we want to ask. One is it important whether the sequence is maintained as an array or as a list? And is it also important, given that it is maintained as an array or a list, whether or not there's some other additional information we know? For example, is it useful for the array to be sorted in ascending order? That is, all the elements go in strictly one sequence from beginning to end, lowest to highest or highest to lowest, or does it matter, does it not matter at all? So here is a very simple Python program to search for a value in an unsorted sequence. So this is similar to what we saw before, where we were looking for the position. We were looking for the position of the first position of a value in a sequence. But since we don't even need the position, we only need true or false. Is it there or is it not? It's a very simple thing. What we do is we loop through all the elements in the sequence and check whether any element is the value that we are looking for. Once we have found it, we can exit. So this exits the function with a value true. And if we have succeeded in going through the entire list, but we have not exited with true, that means we haven't found the thing. So we can unambiguously say after the for that if we have reached this point, we haven't found the value v that we are looking for, and so we should return false. So since we are not looking for the position, we have a much simpler code. If you go back and see the code we wrote for find pos, so there we had to first of all keep track of the position and check the value at position I rather than the value itself. And secondly, when we finished the loop, we had to determine whether or not we had found it or we had not found it. Whether we remember we used a break to get out of the loop the first time we found it. So we used to detect whether we broke or not. If we did have a break, then we had found it. If we did not have a break, we didn't find it. So accordingly, either the value of pos was set or it was not set. And if it is not set, we should make it -1. So that was more complicated. This is very simple. But the main point of this function is that we have no solution to search other than to scan from beginning to end. The only systematic way to find out if v occurs in the sequence or not is to start at the beginning and go till the end and check every value, because we don't have any idea where this value might be. So this will take time in general proportion to the length of the sequence. So we are typically interested in how long this function would take in the worst case. So what is the worst case? Well, of course, one worst case is if we find the value at the end of the list. So v is the last value. Then we have to look at all. But more generally, v is not in the list. Right? If v is not in the list, the only way we can determine that v is not in the list is to check every value and determine that that value is not v. And this property that we have to scan the entire sequence and therefore we have to take time proportional to the sequence to determine whether v is in the sequence or not. It does not matter if the sequence is an array or a list. Whether it's an array or a list, we have to systematically go through every value. The organization of the information doesn't matter. What matters is the fact that there is no additional structure to the information. The information is not sorted in any way. At no point can we give up and say that since we have not seen it so far, we are not going to see it later. On the other hand, if we have a sorted sequence, we have a procedure which would be at least informally familiar to you. So when we search for a word in a dictionary, for example, the dictionary is sorted by alphabetical order of words. So if we are looking for a word, and if we open a page at random, right? Supposing we are looking for the word monkey, and we open the page at we open the dictionary at a page where the values or the words start with I, then we know that M comes after I in the dictionary order of the English alphabet. So we need to only search in the second half of the dictionary after I. We don't have to look at any words before I. So in general, if we have a sequence, the efficient way to search for this value is to first look at the middle value. So we are looking for v. So we check what happens here. So there are three cases. Either we have found it, in which case we are good. If we have not found it, we compare the value we are looking for with what we see over there. If the value we are looking for is smaller than the value we see over there, it must be in this half. On the other hand, if the value we are looking for is bigger, it must be in this half. So we can halve the amount of space to search, and we can be sure that the half we are not going to look at positively doesn't have the value, because we are assuming that this sequence is sorted. Okay, so this is called binary search. This is also, for example, what you do when you play a game like 20 questions. If you played that, when somebody asks you to guess the name of a person they are thinking of, then you might first ask the question whether the person is female. If the person is female, then the answer is yes, then you only need to think about women. If the person says no, then you only need to think about men. So you have men. So you have halved the number of people in your imagination whom you have to think about. At each point, each question then further splits into two groups depending on whether the answer is yes or no. So here is some Python code for binary search. So binary search in general will start with the entire list, and then as we said, it will look at the midpoint and decide on the left. So we'll have to again perform binary search on this. How would we do that? Again, we'll look at the midpoint of this part, and then we'll again look at, say, the midpoint of the next part that we look at, and so on. So in general, binary search is trying to do a binary search for a value in some segment of the list. So we will demarcate that segment using LNR. So we are looking for the slice sequence starting with L and going to R minus 1. We are assuming that sequence is sorted, and we are looking for V there. So first of all, if the slice is empty, right? So this says the slice is empty. That is, we have gone halving the thing, and we have eventually run out of values to look at. Right? The last thing we looked at was a slice of length 1, and we divided it into 2, and we got a slice of length 0. So then we can say that we haven't found it yet, so we are not going to ever find it, and we return false. On the other hand, if the slice is not empty, okay, then what we do is we first compute the midpoint. So an easy way to compute the midpoint is to use this integer division operation. So supposing we have currently the slice from 4 to 7, then at the next point, we will take 11 by 2 integer wise, and we will go to 5. Right? So remember 4, 5, 6, 7. Okay. Right? So we could either choose 6 or 7 next to split it into two parts, because we're going to examine 6 and then look at 4, 5, and 7, or look at 5 and then 4 and 6. So if you do integer division, then we will pick the smaller of the two. So we find the midpoint. Now we check whether the value is the value at that midpoint. If so, we return true. If it is not, then we check whether it is smaller. If so, we continue our search from the existing left point till the left of the midpoint. Now we are using this Python thing that this actually means there's a slice up to mid, and therefore it stops at mid minus 1. So it will not again look at the value we just examined. It will look at everything strictly to its left. Right? So if the value that we are looking for is not the value at the midpoint and it is smaller than the midpoint, you look to the left. Otherwise, you look strictly to the right. You start at mid plus 1 and go up to the current right value. Right? So this is a recursive function. It will keep doing this. At each point, the interval will halve. So eventually, supposing we have a slice of the form just one value, so 5 to 6, for example, then at the next point, right, we will end up having to look at just a slice from 5 to 5 or 6 to 6, and this will give us a slice which is empty, because we will find that the right point and the left point are the same. So how long does the binary search algorithm take? The key point is that each step halves the interval that we are searching, and if we have an empty interval, we get an immediate answer. So the usual way we do this is to record the time taken depending on the size of the sequence or the array or the list. So we've written array here, but it could be sequence in general. So if the sequence has length 0, then it takes only one step, because we just report that it is false. We can't find it if there are no elements left. Otherwise, we have to examine the midpoint. So that takes one abstract step, computing the midpoint and checking whether the value is V. Will collapse it all into one abstract step. And then depending on the answer, remember we're computing worst case. The answer in the worst case is when it is not going to be found in the sequence. So the worst case, it will not be the midpoint. We will have to look at half the sequence. So we will have to again solve a binary search for a new list which is half the length of the old list. So the time taken for n elements is 1 plus the time taken for n by 2 elements. So we want an expression for t of n which satisfies this. So this is what is called a recurrence normally. So what function t of n would satisfy this? One way to do that is to just keep substituting and see what happens. So we start unwinding, as it said. So we have this by the same recurrence should be 1 plus t of n by 4, right? Because I take this and halve it. So t of n is 1 plus t of n by 4. So if we start with 1 plus t of n by 2 and I expand this, okay, then I get 1 plus t of n by 2 squared. And in this case, I'll again get 1 plus 1 plus 1 by t of n by 2 cubed. So in general, after k steps, we will have 1 plus 1 plus 1 k plus 1 times, or k times, and t of n by 2 to the k. Now when do we stop, right? We stop when we actually get t of 0, okay? Or we can also say that for t of 1, it takes one step, okay, just if we want to be careful. So when this expression becomes 1, so when n is equal to 2 to the k. So when is n equal to 2 to the k? This is precisely the definition of log, right? How many times do I have to multiply 2 by itself in order to get n? And that is the value of k that we want. So after log n steps, this term will turn out to be 1. So we will end up with roughly log n times 1 added up. And so we'll get log n steps. Right? So what we are saying is really, if we start with 1,000 values, then the next step we'll end up searching 500, next step 250, next step 125, next step 62, and so on. And if we keep doing this, when will we get to a trivial sequence of length 0 or 1? Well, we keep dividing 1,000 by 2. How many times can we divide 1,000 by 2? That's precisely the log of 1,000 to the base 2. And that's an equivalent definition of log. So this comes back to another point. Now we have said that if we had a sorted sequence of values, we can do this clever binary search. But remember that it requires us to jump in and compute mid, which is fine. And we need to then look at the value at the midpoint. And we are assuming that this computation of mid and comparing the value with the midpoint took a constant amount of time. That's why we said that it is 1 plus tn by 2. This 1 involves computing mid and looking up the sequence at the midpoint. But this can only be done for arrays, because only for arrays can we take a position and jump in and get the value at that position in constant time. It will not work for lists, right? Because we need to look up the sequence at the ith position in constant time. Of course, one important and probably not so obvious thing, if you think about binary search, is that by only looking at a very small number of values, say, so for example, we give you a sorted list of 1,000 entries, as I said, if a value is not there, we only have to search 10 possible entries, because we keep halving after log n, which is about, to remember, the 2 to the 10 is 1024, right? 2 times 2 times 2, 10 times is 1024. So after 10 halvings of 1,000, we would have come down to 0 or 1. So we would definitely be able to tell quickly whether it's there or not. So we only look at 10 values out of 1,000. 990 values we don't look at all, unlike the unsorted case where we have to look at every possible value before we solve it. Right? So it's very efficient binary search, but it requires us to be able to jump into the ith position in constant time. And therefore, if I actually did a binary search on a list, even if it is sorted and not on an array, where I have to start at the 0th position and walk to the ith position by following links, unfortunately, binary search will not give me the expected bonus that I get when I use an array. So having discussed this abstractly, we are of course working in the context of Python. So the question is, are built-in lists in Python, are they lists as we have talked about them, or are they arrays? So actually the documentation would suggest, if you look at the Python documentation, that they are lists, because you do have these expansion and contraction functions. So we saw we can do an append, or we can do a remove of a value, and so on. So they do support these flexible things which are typical of lists. However, Python supports this indexed position, right? So it allows us to look for a to the I, and if you try it out on a large list, you will find that it actually doesn't take that much more time to go to, say, you construct a list of 100,000 elements. You will find it takes no more time to go to the last position as to the first position. As you would normally expect in a list, we said that it should take longer to go to the last position. So although they are lists, as far as we are concerned, we will treat them as arrays when we want to. And just to emphasize how lists work, when we go further in this course, we will actually look at how to implement some data structures, and we will see how to explicitly implement a list with these pointers which point from one element to the other. So for the rest of this course, whenever we look at a Python list, we will kind of implicitly use it as an array. So when we discuss further sorting algorithms and all that, we will do the analysis for the algorithms assuming they are arrays. We will give Python implementations using Python's built-in lists. But as far as we are concerned, these lists are equivalent to arrays for the purpose of this course.